Everyone, welcome back to this channel. In this video, I just want to go over the material for uh, the fourth activity, right? This fourth module on sensors, transducers, and sound. So here I've got the intro slides open. So first, let's talk about sensors. All right, so sound sensors sense sound. We've got one of these KY038 sound sensors in our kit. And so it has two outputs. It's got a digital output and an analog output, right? And this digital output is going to output high if the sound is above some threshold, right? So there's a microphone here, there's presumably some sound in your environment. And if it's above some threshold level, then it'll output high. And so there are actually two LEDs on this board, right? LED 1 is actually just the power LED, so it'll always be on so long as you've applied 5 volts and ground to power the various components on the board. But this bottom LED actually corresponds to the digital output, right? And so if it's too loud, then this LED will be on, right? And if the noise level is below the threshold, then the LED will be off. And you can actually control the threshold using this little potentiometer on here. But there's also an analog output, this AO, which outputs the voltage that's proportional to the sound level. And so we'll be taking a look, we've taken a look during lab at the analog output, just kind of like looking at it on the oscilloscope. Um, so the KY038 has a potentiometer to adjust sensitivity, as I had mentioned. If you're looking at it with the little knob on the bottom right, then in order to increase sensitivity, you turn it clockwise, and to reduce, you turn it counterclockwise. And so you'll need some kind of screwdriver. I know some people were trying to use their fingernails, and it's a little bit more difficult, but I've got a bunch of these flathead screwdrivers if you need one to take home to complete kind of like the project. So I've linked the data sheet for this KY038, and it's got, some example code for you to review. It's pretty straightforward, right? We're just on the analog pin, we can run an analog read, and then a digital pin, we can do a digital read just to get the state of both of those pins. And then it says here that we're taking in 5 volts of power. You pretty much just use the 5 volts coming out of your Arduino. Pretty easy. All right. So the sound that we hear has amplitude and frequency, right? And the amplitude reflects how loud this perceived noise is, and the frequency reflects the tone of the noise, right? So my voice frequency is relatively low, right? So it's probably on the lower end of this acoustic spectrum, but it's not so low that we can't hear it. Um, and so the acoustic spectrum, right, is where we hear noise, and this is from 20 hertz to 20 kilohertz. But there's also these other ranges called infrasound and ultrasound, right? Above our hearing is this ultrasound. And we actually have ultrasonic sensors in our kit as well, right? So this is the HC-SR04 ultrasonic sensor. It's printed right there. And they're typically used to measure distance. It's kind of like the same operating principle as a bat, right? So these bats will transmit a burst of ultrasound. The ultrasound will travel out to, in space, and it'll reflect off of any objects that are in front of it. And then we'll be able to measure, right, the time of flight that it takes for the the ultrasonic wave to reflect off the object and return back to these transducer pairs in order to kind of measure the distance. And so just getting in a little bit more into the theory behind the ultrasonic sensors that we have in our kit. So there's a trigger and an echo pin. And so what happens is the Arduino will send a trigger to the HCSR4, which will tell the HCSR4 module to send out a burst of ultrasound, right? And so here we can see that triggers set. And then there's this sudden 8 cycle burst of ultrasonic, sound from the transmitter of the HCSR4. And then there will be this echo pulse output, which will be high basically until the received wave is seen by the receiver, right? So once we see the wave coming back onto the receiver, then we toggle that high output, this echo output low. And by doing this, we can actually have a signal that's proportional to the distance, right? So as this, we call it the time of flight echo, is longer, the distance will be further, right? And if it's shorter, then there will be an object that's a little bit closer. Um, all right. So now we'll talk a little bit about these transducers. So first off, we're looking at the KY038 sound sensor, and it has a microphone. And microphones are a type of transducer that convert air pressure variations to electricity. And I guess I forgot to kind of define what a transducer is in the first place. Well, so transducers are just things that convert forms of energy, right? So for example, if I go from air pressure to electricity, right? That's two forms of energy that are being converted. So, talking about the microphone again. So, the microphone has two parallel conductive plates, right? It's got this front plate, which is sensitive to the sound waves, right? It'll flex and move corresponding to the incident wave. And then there's also a back plate, which is stationary, right? It doesn't move. It'll only move the front plate based on the sound. And so when we have these two parallel conductive plates, this in essence creates a variable capacitor, right? And by changing the capacitance, we can also change the effective voltage that's kind of seen at the output. So that's how the microphone works. And then getting into the HCSR04, we've got two transducers, as I had mentioned before. So we have one that acts like a microphone in the sense that, right, it's receiving these air pressure variations and converting it to an electric signal, much like the microphone. But we've also got a separate transducer that's actually converting the electric signal into air pressure, kind of like a speaker, right? So it's sending the ultrasonic sound out, and the receiver is acting like a microphone to pick up the variations coming back. Right, and so as I had mentioned, the one that's acting as a microphone is the receiver, and the one acting as a speaker is called the transmitter. All right, so now let's talk about sound. So sound signals typically require filtering, right? And there will always be some sort of noise in any kind of physical system. And, just for an example, as a really basic example, you might have an ambulance going by, and this ambulance has like a really high frequency, presumably, that, maybe you need to remove so that the audio quality is a little bit better. So if our signal is a voltage, we can use what's called an RC filter. And so these are passive in the sense that they actually can't boost the amplitude of the voltage going in. Right? So I've got V in, and over time, this capacitor will charge up in order to match V in, right? And so then the voltage, this V out, can only ever be as big as V in, right? And because of that, you can only get as much voltage as you put in, or yeah, you can only get as much voltage as you put in on the output. And so these RC filters are characterized by what's called a cutoff frequency. And so at this cutoff frequency, we actually have what kind of like the half power point, right? So the output voltage goes with 1 by the square root of 2 of the input voltage, which corresponds to half of the power at the output that you put in. And so for RC filters, the cutoff frequency is given by 1 divided by the quantity 2 pi times RC. And one thing I pointed out kind of like during the lab time is that this product of RC is kind of an interesting phenomenon that it gives units of seconds, right? If I have some kind of frequency, well, this is going to be measured in 1 over seconds, right? And 2 pi doesn't necessarily have a unit associated with it, right? Maybe it has radians, but it's effectively just a number, right? So if I have 1 over seconds, well, then this RC, this product RC, must give units of seconds. So that's just kind of an interesting thing. Um, all right, so getting into LT Spice. So we had looked at LT Spice in a couple pre-labs ago. But today in this activity, we're going to be using it more to analyze filters. So in a nutshell, what you do is you put in right, obviously, first off, you got to build up your circuit, right? So you get a voltage source, a resistor, and a capacitor, and you just put in your R and your C values. And one thing to note is that in LT-Spice, you need to specify mega ohms as meg, right? You can't just put M, that'll register as milliohms. And another thing is that you can put P for pico, and that's going to be 10 to the minus 12. So I built up my circuit here. Um, I've got R to be 1 mega ohm and C to be 100 picofarad. So that should give me 1591 cutoff frequency. And I've set up my AC analysis to do a decade sweep, which just means that on my horizontal axis, I'll be looking at powers of 10, right? So 10 to the 0, which is 1 hertz, 10 to the 1, which is 10 hertz, 10 to the 2, 100 hertz. And I'll be sweeping from 1 hertz to 1 megahertz. And that's how that works there. And I've also set my voltage source to have an AC amplitude of 1, right? So there's going to be effectively a 1 volt peak sine wave coming out of the source, and it'll be changing the frequency based on how I set my analysis here. All right, so if we just run the analysis, we can quickly verify our, half power frequency, right? This minus 3 dB point. So if I use these cursors, I can see that, my 3 dB point is just above 1579 hertz, which, is pretty close to my 1591, which calculated. So that's good. Um, and now just taking a look at the plot in more detail. So this is called a Bode plot, right? And it plots the magnitude and the phase response. So the magnitude response is pretty straightforward. It just shows you how much of the output or how much of the input is getting to the output, right? So we're looking at the ratio. When we plot something in our AC analysis, we're looking at that voltage with respect to whatever our input is. In this case, our input's just a 1 volt peak sine wave. So I'm looking at, right, the ratio of the output to the input. And so here at 0 dB, for example, we've got the case where the output is equal to the input, right? Because if I'm given that the gain in decibels is 20 times the log base 10 of the ratio of the output to the input, well, if the output is equal to the input, right, Vn is equal to Vout, this ratio becomes 1. And the log base of anything, right? Log base anything of 1 gives me 0, right? I'm kind of asking this question, right? 10 to what power gives me 1? And in this case, that's going to be 0, right? Whatever our base is. In this case, our base is 10, but that doesn't matter. Right, so at 0 dB, we have the case where the output is equal to the input. Hmm. And so you can see that the output is equal to the input for a good amount of time. But as our frequency starts to increase, the magnitude starts to roll off, right? And it's decreasing in decibels, which means that, this ratio, the output becomes smaller than the input there. And so we'll be using a function generator, right, to kind of like verify the Bodie plot. With the function generator, we can generate this 1 volt sinusoidal injection voltage, and we can manually change the frequency, um, right? And then use an oscilloscope to actually measure the amplitude at the output, right? Because we know what the amplitude at the input is, so we don't really need to measure that, but it is kind of nice to see that sometimes. And then moving on to sound, I guess one more thing I wanted to make clear is, right, this process of using the function generator and the oscilloscope takes a long time. Right, it's a lot easier to just set up this LT Spice schematic and run the analysis here, and it's kind of incredible what it's doing. So here I'm taking 100 points per decade, which means that, between 1 hertz and 10 hertz, I'm actually taking 100 measurements, right? So that would be like taking 100 measurements on this oscilloscope, right? Maybe I take 1 hertz, 2 hertz, 3 hertz, all the way up to 100 hertz. I'm just manually changing the frequency of this function generator. So I just wanted to build some appreciation of these spice tools, because you will see them a lot, right, in industry and in your academic career as well. So it's good to have that background. All right, so jumping into recordings. So if we have a recording, right, of some kind of sound, maybe an MP3 or a WAV file, we can use MATLAB to load it up and process. Um, in our activity, we're looking at some audio file that's already preloaded into MATLAB. So this is called Handel's Messiah. It's a sample of Handel's Messiah. I think maybe like a 10-second-ish sample. So all we really have to do is call this command load handle, and it'll bring up the data Y and the sampling frequency FS into our workspace. So we can plot what that looks like, right? So this is what Y looks like, and these are just kind of like variations in air pressure, as a function of time, effectively. And so we saw that one of the things that were loaded into the workspace was what's called a sampling frequency, right? FS. And so all this does is it represents how much time has elapsed between samples. And going back to the data, Y, the data is actually just this sequence of values, right? And it's a countable sequence. There are 73,000-ish values here, right? And so we can actually better represent that in time by with knowledge of the sampling frequency, right? So basically, if I have sampling frequency of 8192, then that means that 1 divided by 8192 seconds elapse between these samples. Um, And so MATLAB has this signal processing toolbox, which has a low pass function. We just give it the data. In this case, it's called X, and the cutoff frequency, which they've called fpass, and then the sampling frequency, which was already loaded up into our workspace, capital FS. So you pass those in. Here, I've used a cutoff frequency of 100 hertz, right? And I just pass in my data and the sampling frequency, and I can actually listen to that, right? The effect of low pass filtering the sound, and then I can also look at the data, right? And in this case, we can see that the really rapid variations in air pressure are effectively filtered out, right? So here, kind of like early on, I've got this rapid jump, right? All the way up to zero point 0.8, whatever that unit is there. And we can see that that is no longer present, right? And in fact, I'm only going up to zero point 0.4 at any given time, really. So now getting into kind of like how we realize the sound, right? So we've got speakers in our kit. There's this little passive buzzer, and we can actually control the frequency of a PWM pin, in order to drive this little speaker and make different frequency of noise. Um, and then these are just some notes on extra credit. I won't go over them. I won't go over the C-Park ham cram because that's already passed. But another point is updating your resume because we've got career fair this week. So I've got an example resume here, which includes everything that we've done up through this week in our class here. And you can see it's quite a lot. And I think the way that I've presented this is makes it easy for you to kind of talk through what you've done. So I think it'll look good for any kind of employers here. But I think that's all I had. So, yep, thanks for tuning in. See you guys in the next one.